Water to humanity is an essential need. However, it can also be our worst enemy. According to the Federal Emergency Management Agency, also known as FEMA, floods are America's #1 natural hazard, as they've caused more than $7.1 billion in US flood losses in the last 10 years. Water management takes effect by hydraulic structures, which is designed by civil engineers. Here's a few examples of hydraulic structures built by civil engineers that you may have seen around. You've probably seen many culverts in urbanized areas. Streams get buried underneath man-made structures such as roads, railways, or any other structure to make room for man-made environments. Culverts come in many sizes and shapes, including round, elliptical, and box-like. Some culverts, such as this one, has a natural surface bottom, which makes it able to connect wildlife habitat. The culvert type and shape selection is based on a number of factors, including requirements for hydraulic performance, limitation on upstream water surface elevation, and roadway embankment height. This is engineer Ben Nielsen. Living in Denver, Colorado did not stop him from practicing his favorite hobby, surfing, by taking advantage of the hydraulic jump. A hydraulic jump is a phenomenon which is frequently observed in open channel flows such as rivers and spillways. When liquid at a high velocity discharges into a zone of lower velocity, an abrupt rise occurs in the liquid surface. This is a weir in Melbourne, Australia. A weir is a small barrier that is built across a stream or a river to raise the water level slightly on the upstream side, allowing for water to pool behind them and providing water to flow steadily over the top of the weir itself. Weirs differs from dam in one major way, and that is that the water from the upstream runs over the top of the weir itself, constantly overflowing. The main purpose of building a weir is to measure flow rates, as well as to alter the flow of rivers and, in some designs, to prevent flooding. The equation can be written as Q is equal to C times L times H to the power of 3/2. L is the length of the weir, and H is the height of water over the crest, and C is the discharge coefficient. In flooding occasions, Q, or flow, increases, hence H also increases. But engineers prefer if H did not rise so much. Therefore, they've come up with creative ways to increase L. This is a piano key weir. Note how L was increased within a very confined space. And this is a labyrinth weir in Bravos, Texas. Again, this design allows L to increase in a very creative way. There are plenty of other structures that did not get mentioned in this video, such as tetrapods, jetties, and dams. Finally, pay attention to the following presentation, as well as the example problem coming up at the end of this lecture.